Okay, can you all see that? Okay, awesome. Yeah, so I'm Tia Scarpe. The work I'm going to be talking about today I did as a graduate student at Harvard, working with Daniel Jacob in the Atmospheric Chemistry and Modeling group. I just graduated, so I'm staying as a postdoc over the summer in this group. And this work is really focused on how we can use a combination of bottom-up methods and top-down observations to evaluate national scale estimates of methane emissions. This work was done with many collaborators. I'm going to talk about a couple different projects. So this includes members of our team here at Harvard, and then also I'll talk about kind of some specific collaborators with projects, but I did a lot of work with the Institute of Ecology and Climate Change in Mexico, and then also with Environment and Climate Change Canada. Though I'm not going to really talk much about the Canada work, just for the sake of time today, but feel free to ask me questions on it. Okay. I know it sounds like a lot of you are very familiar with methane emissions, but just I feel like it's always necessary to start with a little policy motivation for the work. So this work really came about because methane emissions are targeted in policy and climate policy, and at the national scale, we really want to think about individual countries. And under the Paris Agreement, individual countries submit nationally determined contributions, or NDCs, and within these, they set kind of climate action plans of what they plan to do about climate change. And this includes setting emission reduction targets. And so almost all countries that have submitted NDCs so far have set targets for addressing methane emissions. Though, for the most part, none of these countries actually say how they're going to do that. And so these targets are set based on a national understanding of emissions, which is established in a national inventory. So individual countries establish their emissions in these national inventories and then report these emissions under the United Nations Framework Convention on Climate Change. And I'll abbreviate that as the UNFCCC from now on. And these emissions are estimated using bottom-up methods, which are based on a process level understanding of emissions, which I'm sure many of you are familiar with. And the key here is that different countries report in different ways. And so the map I'm showing here is just showing that countries can report as Annex 1 countries, which are shown in green, or non-Annex 1 countries shown in purple. And this kind of distinguishes kind of the assumption that countries may have different degrees of information available to them to make these estimates. And so it's assumed that Annex 1 countries have more detailed reports, given that they tend to have more information available to them to submit those reports. And for all of these national inventories, it's important to kind of link to that process level source-based understanding for policy. But doing that is really difficult, and so it can introduce potential uncertainties and biases into these estimates, which is going to hinder policy development. And so kind of, I guess, to give a little information of why this is for these bottom-up methods, if we think about methane sources, for methane, we have a lot of distributed small sources, but then can also emit a lot. I think of an oil and gas well where there's high potential for, or there's potential for high emissions, but not every well is going to emit a lot. And so when we estimate emissions using bottom-up methods, we kind of have two factors. We have an emission factor, which is like your emissions per unit of activity or per source, and then you're going to multiply that by an activity rate over a period of time, and to get your total emission. And when you do this, we can't go out and measure every single source, every single oil and gas well, or every single emission from a cow. And so we have to use a sampled measurement, and then we use an average emission factor. And for this, if we think about our country scale emission estimates, not every country is going to have measurements within their country borders. And so if you're using an emission factor that was measured in a different country, you may be introducing bias into your emission estimate. And so just as an example, if we think of gas production emissions of methane, for countries that don't have their own emission factors, they can use the IPCC provides emission factors. And so here I'm just showing the range of emission factor provided by the IPCC for gas production. So they kind of provide a lower and upper bound. And the issue with this is that it spans an order of magnitude. So countries just have to pick within this bound what they think is best. And so our concern is that, well, this could introduce large biases and uncertainties into our estimate. So how can we use observational data to kind of inform these estimates as an additional constraint? And so within our group, the way we approach this is through inverse modeling, where we start with our policy relevant emissions, and then we use that as a prior estimate of emissions in a chemical transport model like GeoChem. And then that's going to relate our emission to an observed methane concentration in the atmosphere. And then we can compare that modeled atmosphere to our observed atmospheric methane concentration. And so this could be from satellite observations or in situ observations. And then we're going to do a statistical optimization to adjust those emissions to better match the observational data. And so this is going to produce a posterior emission estimate that better matches those observations. And our goal is we want to connect that back to those policy relevant emissions and say, okay, there's disagreement here. Why do we think that is? And so for my kind of PhD work, I really focused on these two endpoints where one, how do we take those national inventories that are reported to UNFCCC and adapt them so that they can be used as a prior estimate of emissions in a model. And then this last part where we're connecting back our inversion results to our bottom-up inventories. As I said, I've done work in Canada and Mexico. I'm not going to talk about Canada today, but this work is hopefully soon to be published. We'll see. And then I'm going to start off by talking about some work that we did on global fossil fuel emissions. So this project is looking at creating a spatially explicit inventory of methane emissions from oil, gas, and coal exploitation activities. This work was done in collaboration with members at Harvard and then also at the DOE's National Energy and Technology Laboratory, and then with NASA JPL as well. So this was really motivated by an observation that was made where we noticed, so typically when we do our inversions in our group, we use the EDGAR global inventory. So this is a global inventory of emissions. And so they have methane specific emission grids by different source sectors. And we noticed when we compared their data for oil and gas to national inventories that use more country specific information, we saw this disagreement in terms of the spatial distribution of emissions. And that's going to be a problem when you go and use this inventory as a prior estimate in your inversion, because you're relying on comparing spatial patterns in a modeled atmosphere and an observed atmosphere. And so we need to have our emissions in the right place. One other concern was that the EDGAR Global database doesn't necessarily match all of the UNFCCC reported emissions, and so it makes it slightly more difficult to connect back to our policy relevant emissions. So for this project, our goal was to start out with those policy relevant emissions and then create a spatial inventory that could be used as a prior estimate of emissions in our inversions. And so we start out with those national emission estimates as reported to the UNFCCC. And so that's what I'm showing on the left here in the map. This is oil and gas emissions for 2016. And we also do coal. I'm just only showing oil and gas here. And so these are taken directly as reported to the UNFCCC, though because some countries don't report emissions or because some countries don't report detailed enough information, we have to supplement those reports with our own estimates using IPCC methods. And so this is kind of the resulting emissions by country. And so then once we have emissions by country and by we have them separated by emission process. Like, for example, we need gas processing emissions separate from gas production, so we can allocate them to the right infrastructure. And so once we have that, then we can distribute emissions within each country using geospatial data. And so on the right, I'm just showing some examples of the geospatial data that we use to distribute emissions, like wells or oil and gas pipelines or facilities like processing plants, refineries, compressor stations, etc. And so once we do all that, then we can produce a grid inventory. And so On the left map here, I'm showing our kind of inventory product that was produced. And so this is oil, gas, and coal exploitation emissions for 2016. And so we started referring to this inventory as the Global Fuel Exploitation Inventory, or GFEI. And so global emissions were just under 100 teragrams based on the UNFCCC reported emissions that we used for this, for GFEI. And since that work was published, we've also worked this last year with an undergraduate, Sheena Grossman at Harvard, to produce an updated version of the inventory, which I'm showing on the right. And so this uses the more recent UNFCCC reported emissions and extends emissions to 2018. And note that the global emissions have decreased by about 20 teragrams per year, and that's mostly related to Russia's updated reported emissions, which I'll talk about in a second. So we just, I guess, to kind of talk about a little bit more of the changes that were made between these two versions. Here I'm showing a comparison by country on top and at the grid scale level on the bottom of between the original version of GFEI and GFEI version 2. And the kind of the important takeaways are that Russia significantly decreased their emissions, which accounts for most of this global total. Sorry, my light went off. And this is slightly offset by Nigeria increasing their emissions reported. And these changes, though, it's important to know, are not like, they're not trends. The countries change their methods for reporting. And so this is kind of, here I'm showing the same comparison in the same year for 2016. So these are kind of updates that they made to their methods used in their reports. Also note that on the bottom, you can see that for Canada and Mexico, there was some within country changes, and that's because we incorporated these new national inventories for Canada and Mexico to use for gridding. And so that's why there's a slight change there in the spatial pattern. So I'll use that as a segue into, I'm going to talk a little bit about kind of this work at the national scale. And so this is kind of a similar project where we're developing a spatially explicit version of policy relevant emissions. And so this is a work that we did in Mexico in collaboration with the Institute of Ecology and Climate Change, which is so they're responsible for reporting emissions to the UNFCCC and putting together Mexico's national inventory. And this is mostly led by Claudia Octaviano in Mexico City. And the project in Canada is similar methods wise. And so feel free at the end to ask me questions on it if you have any. Okay, so for this project, we, similar to the global inventory project, we start out with our national emissions. And so here we use the national inventory from Mexico. And so this is just showing on the left a breakdown of emissions for Mexico. And so emissions are dominated by livestock, though there's significant contributions from fossil fuels and waste sectors. And we need information as specific as possible to sources, because this allows us to kind of distribute the right magnitude of emissions to the right source locations. And so we were able to, through our collaboration with the Institute of Ecology and Climate Change, get very detailed information by source subsector. So I'm not showing all of the subsectors here, but this is kind of a key aspect of working with national agencies in terms of creating these spatial versions of inventories. And so they were able to provide a lot of information that is embedded in the public version of the inventory to us. So once we have that, then we distribute to sources. On the right, I'm just showing a map of point sources. And so this is just, it's not showing methane emissions, it's just showing the density of sources per grid cell. And so this is for point sources, this would include like coal mines or wastewater treatment plants, et cetera. And so then we use those spatial maps to distribute our emissions and produce a gridded inventory product. And so here on the left, I'm just showing that resulting methane emission inventory. And I guess some major takeaways are that in Mexico City, we have the highest emissions. And so it's, as expected, given large population center. But we do note that, there are large contributions from all major sectors, which I'm showing on the right, in this region. And in general, we see the highest emissions in central and eastern Mexico, where we do have these large contributions from all sectors, not, it's not just one emission sector that dominates emissions in a given region. And so then we wanted to also investigate if we could use the bottom-up inventory to kind of learn something about emission sources. And so, take this with a grain of salt, because this is all based on bottom-up information. There's no measurements going into this. But on the left here, I'm showing kind of hotspots that we identified. So these are potential methane emission hotspots that we used our kind of bottom-up inventory information to identify. And so we basically just selected a kind of emission threshold and said, okay, where do we have emissions above this threshold? And then used kind of the geospatial data in our inventory to identify the facilities that were responsible for those emissions. And we ended up finding that, most of our hotspots are related to landfills in Mexico, especially in Mexico City. Some of these are also landfills that aren't actually in operation anymore. And then we also have quite a few fossil fuel related hotspots. And, these grid cells, even just the 16 I'm showing here, actually count for 13% of national emissions. And so they are quite a large fraction that could, achieve significant mitigation efforts if targeted, if our, bottom-up information is accurately reflecting emissions. And so then we additionally did some comparisons with other inventories. And so here I'm just showing on the right an example of our comparison of our work, which is the first bar, to the EDGAR Global Inventory in the second bar, which is, this is the most recent version of EDGAR. And then in the third bar, I'm showing an emission inventory that's specific to Mexico City that kind of the city government produces. And they use, I think, for like air quality modeling. And so we note that, both of our work and the Mexico City inventory show this large solid waste or landfill fraction. And we don't really see this in the EDGAR inventory. And that potentially explains some observed, previous inverse modeling work, and then also just some comparison to observations had seen that Mexico City's emissions were too low when using EDGAR as a prior. And so it's potentially this missing landfill source that could explain that. Okay, so now I'm going to actually transition again to talking about some inverse modeling results. So this is work that we did using kind of, so this wasn't inverse modeling that I did myself. It was work that was done by others in our group. And then we took the results and said, how can we translate this back and use bottom-up information to kind of investigate why we see these discrepancies between top-down and bottom-up. And I'm going to focus on oil and gas here just because that was what we had the most bottom-up information on for this work. Okay, so the key here is that, we're kind of taking these inversion results and relating them back to our prior. And so for these both inversion results that I'm going to talk about used GFA version 1 as a prior estimate of oil and gas emissions. Okay, so first, I just want to give, I guess, a little background for those of you who are, inverse modelers in the crowd and are interested in this. So the two inversion results we use are from Xiao Liu and Zhen Xu. And so these were both global inversions using satellite observations of methane. So for both inversions, they had kind of a similar framework in that they had non-wetland emissions optimized on a horizontal grid, and then wetland emissions were separately optimized for subcontinental regions at a monthly time scale. And then both inversions use prior emissions from GFA version 1, as I said, and use similar emissions for all other sectors as well. And then both inversions use GOSAT observations, but the Liu et al. Inversion here on the right, I'm kind of comparing the two inversions, the differences. So for the Liu et al. Results, they use GOSAT, and they also use Global View Plus. So this is a database from NOAA of in situ observations. And so this plot on the bottom right is showing just an example of what those methane observations look like. And this was really useful to us because we have high emitters in regions that are snow covered for part of the year. And so those in situ observations provide kind of seasonal observations to us in those regions. And another major difference is that, so the Liu et al. Inversion was for multiple years, whereas the Chu et al. Results were only for 1 year. And so this led to also many more observations in the Liu et al. Inversion. The Liu et al. Results was done by 4x5 degree resolution, which is difficult for us when we're trying to get country oil and gas estimates, whereas the Chu et al. Result is at 2x2.5 degree resolution. And this is important because we need to be able to separate sectors in countries. And so we found that, at 4x5 degree resolution, it was difficult to separate emissions between countries in some regions, especially like in like Central Asia, just because, where we have countries that have really non-straight borders or are small countries. And so this resolution makes it kind of difficult to do that. And so here I'm just highlighting, I guess, those advantages and disadvantages. Though I also will note that for the Chu et al. Inversion, there was some assumptions made about wetlands that led to potential aliasing of emissions corrections to other sources. So, we try to not use those inversion results in regions where oil and gas overlaps wetlands. Okay, so here are just showing some of the inversion results. And so I'm showing countries on the y-axis and just methane emissions on the x-axis. And so this is showing the methane emissions by country for the top emitting countries. And in green, I have the Liu et al. Inversion results, and in orange, the Chu et al. Results. And I have in the black X's is GFA version 1. So that was the version of GFA that was used as a prior in the inversion. And then the black pluses are GFA version 2, which are those updated UN reporting emissions. And some major takeaways were that we saw for many of the top emitting countries, our top-down observations show that they're underreporting emissions. And so you can kind of see that our green dots here above our black X's. And so we're showing, and note that this is a log scale that I'm showing these on. So, we have significant underestimates of emissions for these top emitting countries. And, for a lot of these countries, though, there have been, observations of super emitters, for example, in the US and Turkmenistan. And so those could potentially be explaining, why we're underestimating emissions in these national inventories. And we also noted that for, countries like Venezuela, where the oil production dominates, it could be a treatment of what you assume is happening to associated gas in the country that could be leading to these underestimates, where if you assume, there's a certain percentage of waste gas being flared versus vented, that's going to significantly alter your emission estimate. And so it could be that they're underestimating gas venting in heavy oil producing countries. One exception was that for Russia, we saw that Russia was significantly overestimating their emissions, though it seems like their kind of more recent reported emissions were now underestimated. Though we do note that in Russia, because of kind of lack of observations in that region, our posterior emission estimate was only 40% informed by observations. So we're not able to fully constrain their emissions using this kind of inversion setup. And that's a key example of where we don't really want to use our Chu et al. Results because there is significant overlap with wetlands in that region. So we don't really trust those results there. And then if we translate that to global scale emissions, we see that the Liu et al. Results for the inversion show higher total gas emissions at the global scale, which is shown in purple, and compared to both versions of GFA. And this is kind of reflecting that underestimate of country emissions for our top emitting countries. Though for oil, which is shown in yellow, we don't really have much change, but this is kind of reflecting that offset where we have Russia, our top emitter, being decreased and all of these other countries being increased. Kind of zooming out, so now I'm showing more countries for the same plot setup, but I've added in also the IEA estimates. So this is the International Energy Agency. They provide country by country oil and gas emission estimates. And then I've also added EDGAR, and it's not really important to distinguish between the two, but they're both shown in gray. But it's kind of major takeaways are that these other inventories also show an underestimate of emissions for top emitting countries, though in general, the IEA tends to have higher estimates. We also see that there's a large number of countries where our emission estimates in GFA and also kind of our posterior emission estimates are much lower than these other bottom-up inventories indicate. I also wanted to note that for Nigeria, where we saw this kind of significant change in their reported emissions between our two versions of GFA, we note that the posterior emission estimates show agreement with their reported emissions in GFA version 1. So this indicates that now they increased their reported emissions too much now, and so now they're over-reporting. Even though their new emission estimate that's higher, it does agree with these other bottom-up inventories. It disagrees with these top-down observations. Again, just kind of taking that to the global scale. So now I've added EDGAR and IEA to this plot in the third and fourth bars. And as kind of expected, we see that they have much higher gas emission estimates at the global scale because of those overestimates for most countries compared to our posterior emissions. Though we do note that the oil emissions are lower, and this is partly due to Russia's high emission estimates in our prior. Some additional work that we did, this is stepping away from those country-based estimates, but we wanted to learn, for these creating these bottom-up inventories, we have spatial surrogates. We wanted to use the inversion results to see, can we learn something about improved inventories, within countries as well. Here I'm just showing an example. On the top left plot, I'm showing a comparison between our posterior emissions, our GFA version 1, which was used as prior. So this is just showing the difference between top and bottom up. And we see that, I've circled Canada here, that there's a severe underestimate of emissions right at the border with the US, and is also right where the Alberta-Saskatchewan border is. And so we wanted to say, well, what can we explain kind of this severe underestimate with? And so we looked at some different spatial metrics, and we did try also comparing to this version of GFA because it incorporates that new Canada inventory, but we saw the same spatial pattern. And so both of these kind of bottom-up inventories use gas production per well and oil production per well to distribute emissions within the country. And so on the right here, I'm showing on the top row what that looks like in terms of kind of peak activity. So the peak activity is shown in red. And we see that, for gas production, we have peak activity in central, kind of western Alberta. And then for oil, it's kind of scattered slightly at the border of Alberta and Saskatchewan. And so this wouldn't be, that's what we're using to distribute emissions. But when we compare with the peak activity for well count, we see a much different spatial pattern, especially for gas. So the kind of bottom left of these smaller plots here is showing kind of where we have peak well density for gas wells, and it's right at that region where we're underestimating emissions. So this potentially indicates that this underestimate is because we're not properly accounting for the number of infrastructure, and so it indicates that maybe when we're distributing emissions, we need to think about using kind of a combination of metrics to distribute our emissions in future. And so then one kind of additional thing that we wanted to look at was how can we use, we have these source-specific information in our bottom-up inventory, including oil and gas subsectors, and so how can we use that to investigate where countries are maybe going wrong in their emission estimate. And so here I'm actually using those Chu et al. Results. These are the higher resolution inversion results. And so in the top left plot, I'm showing a comparison between, so it's the difference between the posterior emissions from the Chu et al. Inversion and our prior estimate. And we have this severe underestimate of emissions right in South Central Uzbekistan. And so we looked at different the different oil and gas subsectors to try to figure out, okay, well, which one is responsible for this underestimate? And we found that this region is dominated by transmission and processing emissions. And so it's likely that Uzbekistan is choosing too low of an emission factor for their transmission and processing. So it's more kind of midstream activities in their emission estimate. So I will note that in their more recent report to the UN that's used in GFA version 2, they did increase these subsector emissions. And so the bottom left plot here is just showing the difference between those two reported emissions, but not enough to account for this kind of underestimate that we see from observations. In conclusion, through this work, we've created this global fuel exploitation inventory. And so this is a kind of spatially explicit version of our national inventories reported to UNFCCC. And we've updated this using more recent UN reports. And we've also incorporated some new national inventories. And so then these inventories have been used as a prior estimate of emissions in our inversions. And it's shown us that we, based on these comparisons, we see an underestimate of emissions for oil and gas in a lot of our top emitting countries. So, as I said, Russia is a key exception there, that they overestimated their emissions, but have now maybe underestimated their emissions in their most recent report. And thinking about kind of moving forward in the future, we're still investigating kind of explanations for why we see underestimates and overestimates in countries. So I'd love to hear from the crowd too, if anyone has any specific, comments that they'd like to make. One key takeaway that we found was that, this 4x5 degree resolution is really a limiting factor when you try to get to these country by country estimates. So it's really something that we're trying to think about more in the future, moving forward. If our goal is to say something about country estimates of a specific sector, how can we better kind of think about that in our inversion setup before we collect results? So I'll leave it at that and open up to questions.